Good morning. My clock is now showing 9 o'clock, so we're going to go ahead and get started. My name is Mike DeLaCluse, President of Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for level measurement for small tanks and totes. Our presenter today is Herman Coello, Siemens Level Product Manager. In today's webinar, Herman is going to give you an overview of sonic intelligence, the brains behind how the technology works, what's new, what technologies are best suited for smaller tanks, and some do's and don'ts. Herman has more than 20 years of experience with level instrumentation, starting with Miltronics before it was purchased by Siemens. He's been a level application engineer, product marketing manager, and has deep knowledge of all non-contact level technologies. He holds a bachelor's degree in electrical engineering from University of Texas at Arlington. We will be muting the phone lines. If you have any questions, there is a question tool built into GoToWebinar. Please send me the questions and I'll get them answered for you. With that, I'm going to turn it over to Herman. Herman, you with us?
Well, yes.
There we go.
Good morning. Thank you, Mike. Thank you, Mike. Good morning, everyone, and thank you for joining us this morning. As Mike said, I'm the level marketing manager, and what that means that I handle all the level lines in our portfolio, that is ultrasonics, radar, capacitance, and guided radar. This topic today is going to be focused on ultrasonics and geared mostly for small range applications. I will mention some of the other ones. A quick review on capacitance and guided radar just towards the end. But the focus is in ultrasonics, and see alluded already to the discussion. Just a quick review on sonic intelligence, some do's and don'ts, some applications examples, and so forth. Right here is just a quick overview of the portfolio that Siemens offers. Got pressure, temperature, positioners, and this is the area that I'm responsible for. This is capacitance, radar, guided radar, ultrasonics, controllers and transmitters. And again, today we're going to be focusing on transmitters, which are designed for short range. We have weighing and mind meters and such, and we actually target all types of industries, chemicals, oil and gas, water, and also there are a lot of OEM customers that purchase our product to fit it with their solutions. So what is sonic intelligence? Sonic intelligence is based on the time of flight principle, and we can spend a lot of time going through all these, but trying to have a simplified way to explain this, and due to our time, and I think the picture explains it over here. We have a sensor that transmits the pulse, and just like going to the supermarket, we want to know something, how fast you went or how far you went, you measure with the time or the speed. In this case, we know the speed of sound, and the sound travels, comes back, we divide it by 2, and we know based on the time where the level is. Some instruments, some controllers specifically, and some even advanced transmitters like the one you see in the middle. This is also a transmitter, but it's a little bit sophisticated. You can select this product to give you a level, which is the level from the material from 0 to some level. That's the level. Space is the empty space. And some people like to use space because sometimes if they want to take a delivery, then you want to know how much room they have in that tank to take that chemical, that solution, whatever it is, and fill it up. Other people want to know the distance. That's actually the actual distance from the sensor to the product. So this will include the blanking or dead zone plus the space. I separated the transmitters, and I'm happy to tell you this is a new transmitter. We just launched this in at the beginning of the month, actually, in November. It uses the same platform as the Pro. Some of you might know this product. This product was the first transmitter that incorporated a transducer and control and electronics in one piece. This was the very first one. and now we have one, a different look, but essentially with the same functionality. And I'm glad to say that same functionality and everything, and it's coming in at a third lower than the price. Not a third the price, but just 1/3 lower. So it's tremendous savings. The thing about these products, though, they read distance. If you want to not level, you can convert, or not convert, but they invert the 4-to-20. So the output is a 4-to-20 signal. So you can either have 20-to-4 or 4-to-20. If you revert that or convert, inverse that, I should say, then you get level. However, the display that is behind the leads, it will still read distance. Something like this other transmitter over here, you can select level, it will show level. You can select volume, show volume. That just makes it easier for you. But of course, you know, when an instrument can do more, this also costs you more. So the application will dictate what instrument is best suited for you and what needs you have to choose the right application. But today it's not about products. It's about learning a little about sonic intelligence and where you use it. So sonic intelligence is what we use to provide a fast and easy product setup. And you will see today, and what I mean today in the industry, you will see that instruments have become really easy to set up. In cases, some instruments will have wizards you can follow. You don't even have to open the manual. So they gotten so sophisticated, and the algorithms and features on that do a lot of the work that you had to do manually in the past. So you don't have to do that anymore. It's just in special cases. The sonic intelligence and process intelligence give you repeatable and accurate measurements. Flexibility, in the case you want to read level, volume, open channel, all those things. Use sonic intelligence in ultrasonic products, and process intelligence in radar. Here's just an example of what happens in a tank. In a tank, specifically as the level goes up, there's multiple signals. It's not just one signal, not just one signal being sent. And this can be for radar or ultrasonics, or even a transducer that's connected to a controller. The principle is the same. You have a pattern, a signal traveling down to the product. And in some cases, if you're talking about a metallic tank, if you're using a lot of power, to be acoustical noise, it can be acoustical noise from the field stream. All that conversion to some kind of signal is picked up. And if you fill it up, there's more bouncing on the surface of the product into the sealant and back and forth, and that creates multiple signals. So all that is, we need to handle and eliminate that. So that's happening. So we have the pulse traveling down, the signal returning, and there's all the other junk. The noise could be acoustical, could be electrical. We've got to clean that up, because in this particular case, they don't look as big as the actual signal. This is the signal. This is the signal that we're getting from this surface over here. But these other peaks can be confused as echoes, specifically when you have a signal that is not very strong due to the turbulence of the product or something. So this signal is not as strong, and then this might look attractive. So we have to have a way to eliminate them. You don't have to worry about how to do that, but but it's important that you understand that if you have too much of one thing, in case noise, then you might have to do something in order to minimize the effect. So we filter that. So we use some filtering, and you can turn those off and on in some products. We also use some kind of filtering. This red line here represents activity. What that means is a time varying threshold. Simply, what that means is, in order for us to select the right echo, we have to have a way to differentiate between the bad and the good ones. And only the ones that cross this line are considered in the evaluation to see if it's a right echo or not. You can view this, and something like this product over here. We're not going to be talking about this product today, but this one can show it on the screen. Others, you have to view it on a computer, and others don't support that. You know, it all depends how advanced the product is. So we use the algorithms, and I'll mention more about what algorithms are, that they're important. And then that allows you to select the right echo. So this black mark tells me this is my echo. In a nutshell, that's exactly what's going on. And in terms of filtering, you don't have to worry much about it. We do it automatically. Algorithms is another story. I mentioned there are multiple echoes that you can get, and here's an example where you see that this echo crossed the red line, and we have another broad echo that crossed the red line. So those two, and here's another echo that looks like an echo, but it's not big enough to cross the red line, so we don't even evaluate that. And in most applications, 95% of the time, you don't have to do anything. But based on the installation, based on the standpipe and things like that, you might have to make some changes to this. So having a little bit of understanding what that means. Not only having the understanding, but having the capability of doing it, because not everything supports this. You know, but having this can help you maximize or eliminate things that can cause problems in an application. So let me explain a little bit what this is. We're looking over here the criteria, and based on the score every echo receives is the one that's going to be selected. So we're looking at how big an echo is, or the area. You know, we look at the area of the echo, every echo. This is the area underneath the curve. We also look how high it is, or how tall the echo is, and also is it the first echo, or in other words, how close to the face. So we look at all that and start doing a lot of mathematics behind to select the right echo. In the example that I'm showing, you can see that this one in the green circle was selected because it has the most area and it's also the largest. You know, and there are many variations. There are situations where you might want to select the largest only. In some situations, you might select the first only. And I'll show you an example in one of the applications that I will show you, the actual applications. And in some cases, you want to show the area. An area is best used with solids. So LA, or largest in area, is best used for solids. For liquids, BLF, meaning best of largest and first, is best suited for liquids. But there will be situations where you might want just largest or first. And I'll show you a couple of examples of that. You can only select one and give all the weight to one echo, and that will be the one that is forced to be chosen. So, mounting considerations. Before I move into that, I want to say something that you might be familiar with some rule of thumb. You know, some people will tell you it's good to follow a 10-to-1 rule. And the 10-to-1 rule means for every 10 feet you go down, make sure your instrument or your sensor is 1 foot away from the wall. That is a 10-to-1 rule. So if it's 20 feet, then you need to be 2 feet away from the wall. There's two assumptions here. One, that you're dealing with a sensor that has a 12-degree beam angle. And also that the wall that you're looking, the one that you want to be away from, is a smooth wall, not one with a ladder. If you have a ladder, you need to make sure you beam a little bit more away from that ladder. Again, if you're using a 6-degree beam angle, then you can go 20-to-1. But a 10-to-1, if you apply 10-to-1 to most things, you'll be okay. I like to say either one of these. Use a 10-to-1 rule, or 1/3 the diameter of the tank. If you have a process connection that is a 1/3 the diameter of the tank, or the radius of the diameter, or the radius of the tank, I should say, you're in good shape. So here's an example of installations. And they show you and hopefully you can see. You show the different positions, and my question to you is, what is the best location based on what I just told you? Is it 1, 2, 3, or 4? You know, and so 1 is too close to the tank wall, and if that is the only location you can install it, we could work with that and do some suppression of the signal, but it takes a little bit more work. 2, that's practically what I was saying earlier, is about 1/3 the radius, roughly. And that's a good place. That's a good place to install. 3, we can work with 3, but now we get in this parabolic effect. And what that means is there's going to be a focal point, typically around 80 or 85%, where the focal point is going to happen. You're going to get signals that will add up and signals that will cancel out, but some of the signals that add up, they double or triple in size, and they're more attractive, and they look farther away. So you might have a situation, if you ever have this situation where you say, you know what, I'm almost full, but my reading or my output is telling me that I'm 20% full. That's wrong. It could be that you're in the middle, you catch in a multiple echo. So the ideal thing to do is move it away from the center. But if you don't have a process connection, then you use the algorithm and tell the unit, lock on the first echo, not on the largest, because the multiple echoes tend to be larger because they're adding. So that's what you want to do. 4 you don't want to use because the field pipe will be on this side in this case, and it will interfere with the signal path. And we don't want that. It will work when there's nothing coming in, and it will fail when product starts coming in. Another key point is all non-contacting devices. That is, radar would be one, ultrasonics would be another. They require a blind zone or a blanking zone. And it depends on the model. Some can be 12 inches, some can be 10, some can be 2 feet. But don't bring your product inside the blanking zone, because then you start entering an area of contention. So if that is the blind zone, the big area, here's your product, and as long as you stay below the blind zone, you're fine. Again, if you enter in the blind zone or blanking zone, the behavior can be random, and the more likely you say there's something wrong with the product, and the reality is the material is entering that area. This is one of the reasons, a place where if you have a small tank, you might consider using guided wave radar, because guided wave radar allows you to bring the level higher in capacitance, and I will mention a couple of things about capacitance later. If you're dealing with a small tote or tank, and you cannot afford to lose 10 inches or 12 inches of that tank space, think of using guided wave radar or capacitance. That allow you to get to, there's models that allow you to get to the very top, depending on the model. They could be more expensive, and today the price has come down, so it's a feasible solution. But that's one thing. A small tank will require, if you're dealing with something like a barrel, more likely you want capacitance. But if you're dealing with a 10 feet tank, more likely you have space to spare, and having a blind zone is not an issue. You also can have a standpipe, but we want to minimize the standpipes or process connections length or height. They bring other problems. We can work with them, but they're not a 1, 2, 3 situation. Here you can see now that the level went up a little bit, and now here's the actual echo. This is the actual echo over here, but now we start tracking outside, so this is not wrong. So the actual distance is here, but you might get a reading saying that it's here, which is wrong. And it gets worse as you get even closer. The level gets higher, and now the signal goes all crazy, and multiple echoes are occurring, and now we're deselected from this signal over here, and we're reading here. And what happens is, why do we need this space? Is because in ultrasonics, there is a crystal, being excited by voltage to resonate and send a signal and travel. In other words, it's an echo. And it requires some time to reach a steady state. In other words, it requires some time to settle down and be able to receive, to be received. But when it's happening too quickly, the crystal still is excited, so it's still trying to reach steady state, while another signal comes back from the outside and it gives it more excitement and it never reaches a steady state. So that's where the contention begins. That I could express this in this way, like when you have a dialogue, it's best when one person talks and the other listens, so the whole message goes through. When both talk, there's some signal that, for some conversation, some words will be understood and some won't, and the message is convoluted and you lose a clear message. So the same with this. That's what we want to make sure that we don't interfere with the blanking zone or blind zone. Other things to consider. If you're dealing with applications that are really hot, above 200 Fahrenheit, or they're vapors, solvents are those that create vapors. They can be vapors that are due to the process, or some that happen in summertime because the product is overheated, and specifically in Texas, Arizona, places that are really hot, vapors can occur in some solvents. Or if you're dealing with severe dust or slightly foamy surface. And I say slightly because the best technology, not the solution, but the best technology for foam when it gets a little heavy is guided by radar, single rod. That's what you want. It's not a solution. Foam is a problematic issue for technologies. Also, if you're using vacuum or extreme low temperatures, like cryogenic, ultrasonics is not suited for that. These are radar applications. So knowing this, you know where you can use ultrasonics. So stay away from volatiles, vapors, high temperatures, and pretty much everything else you can do with ultrasonics. Some application examples, and I will show you some of the products that are good for those small vessels. And this is the one that I was telling you earlier, the LU150. It's a two-wire device. It's good for 16 feet range. You can program that to be with 2 buttons. You set it up for 4 and 20, and it can be 2 feet to 3 feet or 2 feet to 10 feet, whatever you need. 140 Fahrenheit maximum temperature. And it has, even though it's a new product, it's based on the platform of the product that has a lot of experience. So the functionality is the same. And it does have a better enclosure housing. This one has an IP68 housing, meaning that it can be submerged under water for 2 feet down for 24 hours, and there will not be any ingress in the product. While in submergence, the product doesn't work because the speed of sound travels way faster. But what that means is once the condition is corrected, your instrument is ready to roll. This can be used in chemical storage tanks, solvents, additives. Again, if you have solvents that don't, and like I said, inside a building where the vapors don't exist, you can use it there. Flotation cells. This is mostly for mining. If you have questions about that, I can come back to this picture and explain something about that. These are mud drilling, OEM applications. And here's one application that is corrosive media, sulfuric acid. This product has a Kyner face or cone, quite compatible with that media, etc. Relatively speaking, it's a simple application. The fact that it's there's some condensation, I don't know if you can appreciate that. The mechanical action of the crystal tends to push that moisture away and provide a reliable measurement. If the condition of moisture gets to be too much, then you got to find other ways to keep that moisture away from the sensors. But the key here is that it's compatible with corrosive media, and it's an expensive solution, like I mentioned earlier. This is an open channel. I know that it's closed tanks and totes, but just to show you, this was using an open channel. It's not the ideal solution for open channel, but some customers don't want to spend the money or don't have the budget for that. So in this case, you take the level of measurement, and the conversion of flow is done at the PLC. Here's another one for that filter bed. Some foam on the bottom, we can handle that. If you have a little turbulence, most instruments, including radar, will have problems with a lot of turbulence because this foam can get really thick, and that can be a problem. I will need to have a visual that things change with the conditions. If you add a lot of turbulence to this application, the foam will be crazy. But in this particular case, this unit was performing flawlessly. Here's a situation where more drilling, where they were using floats, and it will build up. So there was a little mechanical wear and tear, a little clogging, and they decided to go to non-contacting. And that's what you want in situations when you don't want the product, your material, to come in contact with the sensor. That's what you want ultrasonics or radar, because it's non-contacting, so you keep the sensor clean and you don't invade the process, and you don't have the issues that are associated with any contacting devices. That includes floats, guided with radar capacitance. The LU150 can be used for this application, and it can be used for that. The ProView, this has been in the market for a good while, for a few years. I want just to give you an overview. It's a two-wire device, 20 or 40 feet. This one has heart, and I'm mentioning here because I got some examples. Here's an example where this unit was installed in the middle of the tank, and I said earlier that's not a good place to do that. So being that that's the only place you can do this, that's where it required to change the algorithm to first to prevent the unit from locking on the multiple echoes. So that's where you use the algorithms. Most cases, if you install this someplace over here, you will have to do that. Here's another situation, very small tanks. There's actually, some of these tanks are, in this case, this is 3.5 feet, some are 16 feet. More of a challenge, notice that they have a long nozzle over here, big nozzle. They're not a good idea, but in this particular case, they were able to use the algorithms and the blanking to blank some of the blipping that occurs at the end of the nozzle. So there's ways that you can use these instruments for small tanks, and so this is for a ski manufacturer, and that's why the solution they've been using that quite a bit. This is a biodiesel application. They use this particular product. You can see the display because they have tanks that vary in length, from 25 to 40 feet. And in this particular case, this is a Profibus network. This is ammonium nitrate. It's like a wax product. And in this case, the unit is right on really close to the tank wall, and the nozzle's a little high, and you can see the ringing and all the other interference from being too close to the tank wall and a high nozzle, all these. But notice that the red line is being shaped around. That means it was tuned out. It was tuned to tune out the unwanted response. And right here, you have the echo selected. So that's what having advanced algorithms gives you. It's not just a level of measurement, but you can make modifications to make things work. Because of this, they don't want spilling, they put capacitance also as a high level warning. It's always when you want to prevent spills, it's good to use an alternate technology. In other words, don't use the same technology, use something different. This was an interesting one, another small application, really short application, and very close to the wall with some lip over here, and they needed some tuning to prevent that. But more importantly, this one couldn't be done with radar because the electrical of this product is too low, and also it's a very heavy sludge and creates steep angles, so the reflection of the signal is deflected too much. First, capacitance. Let's change a little bit of capacitance. Capacitance is good for small tanks, small totes. The one thing to consider with capacitance is it's essentially a capacitor. You know, that the wall is one plate, and the actual rod is the electrode. In between is what we're trying to read. In this case, it's electric. So when the product moves up and down, that's what we're reading, the electric, and we convert that into a signal. The challenge with capacitance is if you're dealing with low electric products, and is that electric changes, your output also changes. So that's, if you're using capacitance, make sure that you're using it with a product that is very consistent. If today you have a product that has an electrical 6, and tomorrow you mix it and you have a product that has an electrical 10, your output is going to change even though the level is the same. You don't want that. So if you quality call for a consistent product and it's a small tank, capacitance will be the way. But if there's some changes in the recipe, tomorrow you have to add something else, you'll be finding yourself tuning capacitance quite a bit. So if you need that, if you need to fill up the tank and capacitance is not a viable solution, then you can go to guided wave radar. Guided wave radar is different than capacitance. The signal travels on the rod and it's back and up and down. It can even be used for interface of oil and water, for instance. But it handles high temperatures, high pressures, and if that electric changes, if the electric is 5 and it goes to 20, it doesn't matter. You still get a signal that is consistent with what the level is. So you prevent those fluctuations that you will see with capacitance. And the disadvantage of guided wave radar would be that it's contacting. So you have buildup. If you have a product that builds up, you have a problem with that. If you're dealing with solids, there's a lot of wear and tear. And if it's a tall silo or tank, there are a lot of pull forces, and we'd rather use radar for that instead of using guided wave radar. You know, so we don't want broken cables going down the system. So essentially, time of flight is just that. You know, you send a signal, it travels, it can be acoustic or electromagnetic wave, comes back, you determine the level based on the time of flight. You know, they're easy to install these days. They're easy to program and maintain. They're non-contacting, so there's no maintenance associated with them, and they give you accurate level measurement. Because in ultrasonics, although it's dependent on sound, there's a temperature sensor in these sensors to compensate so the sound is adjusted. So that is something that we're able to do with ultrasonics to compensate for sound. I'll be here for a few minutes. Thank you for your time, and I'm here to answer any questions you might have. Thank you very much.
Herman, thank you for your presentation. I'm going to take the screen back and put up another slide here. Here's a couple of places you can go for more information on these products. If you have any specific application questions, which I don't see that any have come in, you can feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, feel free to ask for me, Mike D. LaCluse, and I'll make sure that you get taken care of. You've also got my email address, so feel free to send me an email as well. Our next webinar is coming up Thursday, December 10th at 9 a.m. It'll be presented by another Siemens product manager, John Drenette. John will be presenting the basics of belt scales, a topic he's extremely knowledgeable on, having had 10 years of experience as a product manager, and prior to that he had field service experience. So if you have dry powder weighing applications that you're struggling with, you won't want to miss this webinar. An invitation in an email will be coming soon. With that, we don't have any further questions, so we'll go ahead and end the webinar. Again, if you do have any, feel free to send me an email and I'll make sure they get answered. Herman, thank you very much for your presentation.
Thank you, Mike. Have a good weekend.
All right, thank you.